So we'll go to Robert Bagdigian from Marshall Space Flight Center. 30 years of experience in ECLSS. I believe he started working ECLSS on Space Station Freedom. Right? So really honored to have all of these folks here today. Thank you very much, Robert.
Thank you. All right, thank you. I do realize I am the last person between you and the social, so, but it reminds me of some really good advice I got early in my career when one of my supervisors said, if you're ever the last person presenting in a meeting, you need to figure out some way to grab your audience's attention and make them want to stick around through your whole talk. So let me just let you know up front that within my charts, I have a couple of charts that talk about pee and poop. So if you want to hear about that, hang in there. So I'm going to talk a little bit about what we're doing. Again, I work life support, environmental control and life support at NASA. I've worked just about my whole career there. I consider myself very, very fortunate in that I came into NASA right when Space Station, at that time Space Station Freedom, was just getting kicked off, and I have been able to experience the entire life cycle of taking some life support technologies and seeing them fruition and see them operating on Space Station, and can see the evidences of good decisions I made in the past and not so good decisions in the past, and learning about how to do things better and make these types of systems more reliable for the future. It's an exciting time at NASA, and being a life support guy in particular, I was very happy to see the very first space policy directive coming out of the administration recently was about human space exploration, near and dear to my heart as a life support engineer. And within there, I'm sure you've all seen it, but it talks about NASA and America leading, needing to lead innovation, sustainable programs that combine not just a government-directed, government-led type of development, but also begins leveraging a lot of the innovation and new ways of doing business that are coming out of the commercial partners, and stitching that together for, not to sound corny or anything, but for the benefit of humanity. There was a chart earlier this afternoon, somebody was showing the projected, I forget what the numbers were, but a traditional government-led type of program, $500 billion, but you start buying that cost down by sharing and making use of the shared interest you might have with other stakeholders, and by combining and stitching together the interests of a multitude of stakeholders, you can begin putting together an affordable program that benefits more than just the government. So, very important part, but that human exploration policy does not stand by itself. It's actually related to the other two. First, on streamlining regulations, on the commercial use of space. I'm from the government, I'm here to help, kind of thing. The policy directives talks about and recognizes that federal regulations are among the things that can impede the progress that can be made out in the private sector. Down at my level as a NASA engineer, it's not so much federal regulations, but the engineering standards that myself and my colleagues, we've been working towards for years. And when we begin engaging with partners, some non-traditional partners, they say, well, why are you doing it that way? And it really makes us pause and think about, well, why are we doing it? Yeah, we've been doing it that way for a couple of decades now, but what's the root of that standard, that requirement? And we're hopefully we're providing some value to some of our non-traditional partners to maybe step up their game a little bit and appreciate some of the complexities that isn't immediately obvious. So I think there's benefit both ways. And then finally, hopefully, what we're doing will lead to a lot of activity in space, much more than we have now, hopefully much more than we can even imagine right now. And just like managing traffic here on the ground, there's need to manage traffic in space. So It's all related. We are very much wanting to move towards an open architecture, enabling an open architecture in space. Space station is really has been and continues to be a tremendous learning tool for us on what that means and how to do that. Space station, as you know, it's not a U.S. only government-directed venture right now. We do have a vibrant partnership with our international partners, the Russians, the Japanese, and Europeans, Canadians as well. All provide important contributions to sustaining and operating that space station. We're also relying now quite a bit on commercial partners. We have Northrop Grumman, SpaceX, right now providing logistics support to space station. Sierra Nevada is coming along behind them. And we hopefully within the next year or so, we'll also have our commercial partners, SpaceX and Boeing in particular, being able to give us alternate means of getting crew to the space station. So, and given the recent problems the Russians had with their last crew launch, that again reiterates the importance of having at our disposal multiple ways of getting people up to space and back. But this is all well and good. It supports space station, and we're reaping the benefits of that. But all this kind of collaboration, this partnership things, we think very definitely will feed forward into architecture in the future where we have multiple providers providing multiple capabilities that can then combine to give us a much more robust and sustainable space architecture. The plan right now is to go about this in hopefully a logical and incremental fashion. Today we've got in LEO, we're in the early stages of developing a LEO commercial market, a human-based LEO commercial market. On space station, we're using space station aggressively for some technology development. And we're also continuing to learn a lot about human medicine and the effects of long duration microgravity environment on humans and what we need to do to mitigate those types of effects. And in parallel with that, there's ongoing work with lunar discovery and exploration through a number of lunar robotic missions. By the early 2020s, we'll have SLS and Orion online. We'll be in the early stages of building up the Gateway, which will provide a stepping stone to the lunar surface and a staging point to begin sending missions, human missions, ultimately to Mars. Continuing on late 2020s, we'll have Gateway in lunar orbit. We'll be developing larger lunar landers, progressing ultimately to human-class landers, and be taking advantage of some Mars sample return missions. By the late 2030s, we'll have human and robotic lunar surface ops, routine operations in place, prepping for Mars missions, with the ultimate prize being human Mars missions in the late 30s. To make all this work, the last thing we want to do is to end up with square pegs that we need to fit into round holes. So we've been spending a fair amount of effort lately on what we call developing interoperability standards. These standards are not intended to define the how something gets designed, but more importantly, to define if you're going to build a widget and I'm going to build a widget, we want those widgets to work together. These are some of the features that we need to make sure both of our widgets include, so that we can plug and play it, and they are compatible down the road. We've developed the initial drafts of these interoperability standards internally in NASA that engage our international partners in developing those. But we're not stopping there. Taking advantage of kind of the the strength of crowdsource thinking and visionary ideas. We've actually published those draft interoperability standards out on the internet, www.internationaldeepspacestandards.com. And you'll notice it's a .com, not a .gov type of website. And they're out there, and the public is invited to look at and comment and suggest. And we are very open and eager to see what we get, because I'm sure there are ideas out there that we haven't thought of. We've got strategic principles that have been guiding how we go about doing our work and judging some of our plans against those strategic principles. First and foremost, and I think you've heard this as a recurring theme a little bit so far today, and we'll continue to do so, is we have to be fiscally real in our expectations. Honestly, we have our NASA budget has been relatively stable, which in the current environment compared to other programs or other agencies, that hasn't been the case. So we do have good support in the public sphere, in Congress, but realistically, even though our goals are lofty, we are not planning and are not expecting to have any lofty increases in our budget. So what we need to do is to make sure that what we plan to do, we can afford to do, given the size of budgets that we currently have today. One way to make that work is to take maximum advantage of international and commercial partnerships. Again, take the combined interest of disparate parties, whether they're other international governments or other commercial entities that might want to have some market-driven opportunities, and do what we can to bring all those together so that we all get more than we could have got if we ran for the cliff ourselves. Scientific exploration continues to be important with everything we do. It's a big reason of why we're out there exploring. Trying to make sure we do the proper balance of technology, push and pull. You know, there's always people on, you can find plenty on each end of the spectrum, but ultimately it's probably a healthy mix of both, depending on what problem it is you're needing to solve and what the constraints are. This is all going to have to be done gradually. This build-up will be built gradually, again, partly driven or mostly driven by the fiscal realism we're trying to live within. We want the architecture to be open, as I mentioned, and it's very important that it need to be resilient. If you look back at any of our programs, Space Station is a great example. Where Space Station today is not where any of us envisioned it was, certainly back in the Space Station Freedom program, or even the earliest days of the International Space Station program. That platform has evolved and continues to evolve, and probably this time in early 2020s will probably be things about Space Station that are different than we even thought of today. So we need that resiliency, we need that flexibility. The political climate is always changing, and we need to make sure that we can be resilient and react accordingly. There are certain basic things we need to do to keep people alive in space for all missions. And some of these, you know, if you've taken any sort of biology or human physiology or just live every day, you can pretty much figure out. We obviously have to supply oxygen, we remove carbon dioxide, we have to control the cabin pressure. On Space Station, we do that to be in close to Earth atmosphere type of sea level pressure as we can, but there are some architecture advantages of going to reduced pressures if you think you're going to be doing a lot of EVA. We have to control the atmosphere composition, its purity. If you're in a very tightly closed, tightly sealed environment, and you know things build up over time. You know, we're all humans. We're a little bit funky at times, and so we got to make sure that we keep that atmosphere as pure as we can. We got to control temperature and humidity. We need to respond to and recover to environmental emergencies, whether it be fires or spills of hazardous materials or things like that. We need to ventilate the cabin. In microgravity, you don't get natural convection that's continually recirculating the air from buoyancy-driven convection, so we got to make sure all parts of the vehicle are adequately ventilated. Have to monitor the cabin environment, detect and suppress fires, collect, stabilize, and dispose of waste, supply water, and supply food. That, in general, no matter whether those types of things, whether you're going for 1 day or a year or 3 years, all those things need to be done. If you look beyond that and start thinking about longer missions, it then may become beneficial to do things like recycle oxygen, recycle water, or produce food. The average person, all of us sitting here today, you might be surprised by some of these numbers, but on average, every one of us takes in about 11 pounds of mass per day. That's a combination of oxygen that you breathe in, water that you consume either as liquid water or as part of the food you eat, and then solid mass that's part of the food. What comes in, ultimately, on average, must come out, so that means we also have about 11 pounds. Each of us generates 1,100 pounds of output per day as well. That needs to, in a closed environment, we need to be doing something with. If you do the math, it's just simple arithmetic. That means for any one person over the course of 1 year, we're talking about 4,000 pounds of mass needing to be supplied to that person, and about 4,000 pounds of waste needing to be managed or dealt with. That's what we call an open loop kind of architecture. Pretty reliable, pretty easy to plan for, but it's very mass intensive. But if you take that same person and instead try to start doing something more useful with these byproducts, for example, on space station, we take carbon dioxide, we put it through an oxygen recovery system, we recover that oxygen or a portion of that oxygen from the carbon dioxide, give that oxygen back to the crew. We can take and we dispose of the carbon rather than as carbon dioxide, but on space station we're disposing of it as methane. We can take some of the water, in this case humidity, that we collect out of the cabin atmosphere and urine, put it through a water recovery system, give that purified water back to the crew. And by doing that, given the state of the art that we have on space station today, we've now reduced that 4,000 pounds per year supply and 4,000 pounds of waste disposal down to we reduced that by about 70% or so. Pretty good for something like space station. Even though we're in space, we're still in relatively close proximity. We do have relatively routine resupply capabilities we can make up for these types of shortages, but still not quite good enough for deep space exploration when we no longer have that supply chain from the ground. And so things we're working on today is to increase the level, what we call the level of loop closure. Right now today, if you go to a lower level of detail in this chart, we're recovering about 90 to 92% of the water that's available to us in these different water sources we have in our waste, and recovering a little less than 50% of the oxygen. We're trying to get that oxygen recovery up at least to 75% and trying to get that water recovery up to 98, 99% overall. So when does it make sense to close the loop, and by how much? This is a idealized depiction of how we go about that thought process. If you take any mission duration, and again, this is not going to be to scale, you take any mission duration, and you say, well, if I want to do an open loop configuration, I just want to supply all the water, all the oxygen that the crew is going to need. If it was a 0-day mission, I don't need any. If it's a 1-day mission, I need a little bit. If it's a 100-day mission, I need more than that. It's a relatively linear relationship. Pretty easy to figure out. But if you mission duration, the downside is your mission durations get really long, your masses can start becoming prohibitive. So what we do on space station, which represents our state of the art, is we have what we call a regenerative system, and it's not completely regenerative, like I implied on the previous chart. We're not 100% closed, but we're call it 70% closed. But in order to do that, we have to put on the vehicle on day 0. We have to put the mass of the system that's going to do our recovery for us, and a certain complement of spares that we think is going to be sufficient to last whatever that mission duration is. And in the early part, or for particular short duration missions, that mass typically exceeds the mass that you could have more simply just loaded onto the vehicle as oxygen, water, and tankage. But at some point, as the planned mission duration goes out, you get to this break-even point, beyond which it begins making sense to begin implementing an oxygen or water recovery system or both. A lot of times, if you look at papers, this kind of break-even chart is shown as kind of a deterministic. This is 1 day longer than that break-even point. It now makes sense, but unfortunately, there's a lot of uncertainty in that. The uncertainty is driven by a lot of things. A lot of it is driven by what is your experience so far with that technology that you use, and what's the mean time between failure, how much confidence do we have in that mean time between failure, how much do we need to protect against unexpected failures of those systems. And so we get this uncertainty that then kind of pushes out the mission duration at which you would then begin getting enough confidence that says, yeah, it still makes sense to start closing these loops. And as I mentioned, we're continuing to look at additional capabilities that would allow us to kind of lower the slope of that line, which would represent increased levels of closure, increase reliability, which would decrease our reliance on spares. But again, that also has levels of uncertainty associated with it. So the answer to the question is, when does it make sense? Well, the answer is, well, it kind of depends. It depends on your crew size and mission duration, which are very straightforward, but where it really gets fuzzy and where we really get value from the decade or so of ISS operational experience is figuring out what is the uncertainty band, what drives those uncertainty bands, and what can we do to reduce those uncertainty bands to make these what I call mission supportability risk trades. Do we want to bring 3 spares of this thing, or 4 spares, or 5 spares of it? And it all comes down to risk. You can never put everything on the vehicle that you want to put on there. Each additional piece of ECLSS hardware you put on there is some other piece, some other spare of somebody else's system that you can't. So, as I mentioned, we got space station great test bed for us, but it is what we call still Earth reliant. Space station was originally designed and conceived as predominantly a scientific platform. We did not want the crew to be burdening the crew with having to do a lot of maintenance, so we packaged our equipment into orbital replacement units, which were relatively straightforward to change out when something failed, but things were subdivided at a very high level, and so you wound up changing out when a small sensor inside an ORU failed out, you wound up having to change out that entire ORU. By the way, what's pictured there is the distiller part of our urine processor assembly. We're distilling urine in microgravity to to compensate for the lack of gravity, which we need for that phase separation. We actually do that distillation in a rotary distiller, which winds up, if you saw a cutaway of that, it gets kind of complex inside. We make a fairly abundant use of expendable filters. Space station is a closed environment. We do control that environment as best we can, but it's very important to us to make sure that we keep an eye on that environment and make sure that that environment is not creeping over into characteristics that could then become hazardous to the crew. So we have the capability, fortunately, to be able to collect samples and get those samples periodically returned to the ground for in-depth analyses. We have some general analysis capability on station, but nothing close to what we can do on the ground. We're blessed with being able to stock and supply a large amount of makeup consumables. Those are bags of stored water that we have set aside on station for those situations when our water recovery system is not operating. And within the last couple of years, we've been beginning to learn about plants. Obviously, plants play a big part of keeping our environment habitable for us here on Earth. They're also an very important food source for us. Doing that on a spacecraft where you're very limited in volume that you can dedicate to plants is a challenge. So we're beginning to learn about that and beginning to learn what effect that environment has on the plants themselves. From there, the plan is, when we get to something like Gateway, one of our first priorities is to demonstrate that we've been able to increase the level of autonomy. So rather than replacing large ORUs, we're working towards having much more significant on-orbit repair capability. We want to be able to do things like regenerate filters rather than dispose of filters. We're trying to enhance the ability that we have to have the environment analyzed in depth on orbit without having to send samples back to the ground. We're trying to squeeze, again, that last few percent of water out of waste and oxygen from carbon dioxide. I guess it doesn't show up too well on the screen. That's actually a picture of urine, the residue that's left behind when you boil urine down to the last few percent. And you don't want to do that experiment in your mother's kitchen, that's for sure. It stinks. And then get to the point where we're not just studying plants, but we're actually making routine use of them, not as the only diet supply for the crew, but begins using that to supplement the crew's diet and nutrition on orbit. And then finally, as I get off the chart stage, ultimately what we'd like to be able to get to is to make more use of the ability to manufacture equipment. There's a lot of experimentation on space station right now with 3D printing of items and objects. We're working very closely with our counterparts in those projects to help them understand, from an ECLS perspective, what are the kinds of things that typically break down in our systems, and gee, wouldn't it be nice if you could manufacture those kind of things? It's a big challenge, but the benefits could be substantial if we can make it work. Certainly when we get to Mars, maybe some of the other planetary surfaces, we need to make sure that we've thought through planetary protection, both protecting the planet and then protecting the crew and the crew's return to Earth. So we're not that we're protecting both directions. We'd like our vehicles, from an ECLS perspective, to be much more autonomous than they are. Without needing a lot of crew attention and without needing the marching army of ground controllers that we have today, monitoring those systems and debating what the data is telling us and having to make those decisions day in, day out about how to operate the system the next day, the next week. We've heard a number of speakers today talk about in situ resource utilization. That can have a big impact on what we need to do on the life support sides of things, especially if we're making oxygen for propellant. The oxygen we need for life support is a small drop in the bucket if you're making propellant quantities of oxygen. And then finally, way on down the road, we use crops not just as a dietary supplement, but as a main part of their nutritional needs. So I think that's my last chart. So I think that means you're at break time or social time. So have at it.